Article 430.22c of the National Electrical Code allows the rating of circuits supplying intermittent duty motors to be reduced by up to 15%, which equates to 85% of the motor rating. The time duty of the motor is determined by the ratio of its operating time to its total operating cycle time. Article 430.32a of the National Electrical Code permits the use of a circuit breaker as thermal protection for motors with that built-in thermal protection, provided the circuit breaker ampacity does not exceed 250% of the motor nameplate current rating. This assumes that the circuit breaker is properly sized for the motor's locked rotor current. To apply these concepts, let's consider an example with 12 motors, each rated at 2 horsepower, 208 volts, intermittent duty. First, we calculate the motor rating in watts. Since 1 horsepower equals 746 watts, 2 horsepower is equal to 2 times 746 watts, which equals 1492 watts. Next, we apply the reduced rating of 85% for intermittent duty. 1492 watts times 0.85 equals 1268.2 watts. To determine the branch circuit ampacity, we divide the reduced wattage by the voltage. 1268.2 watts divided by 208 volts equals approximately 6.1 amps. To size the circuit breaker, we multiply the branch circuit ampacity by 250%. 6.1 amps times 2.5 equals 15.25 amps. Therefore, a 15 amp circuit breaker can be used to provide both circuit protection and thermal protection for each motor. When working with intermittent duty motors, remember these key points. Firstly, understand the motor's duty cycle and its impact on ampacity calculations. Secondly, consult Article 430 of the National Electrical Code for specific requirements and allowances. Thirdly, correctly size the circuit breaker to provide both overcurrent and thermal protection. Fourthly, always verify the motor's locked rotor current to ensure the circuit breaker can handle it. Fifthly, ensure all wiring and components are rated for the calculated ampacity and voltage. Sixthly, use appropriate wire gauges and conduit sizes to prevent overheating and voltage drop. Seventhly, label each circuit clearly indicating the motor it serves. Eighthly, double-check all connections to ensure they are secure and properly torqued. Ninthly, follow all applicable local and national electrical codes. Tenthly, employ a licensed electrician to perform the installation and verify its compliance with safety standards. Now let's delve a little deeper into the National Electrical Code requirements for motor circuits. Article 430 covers motors, motor circuits, and controllers. It provides guidelines for selecting the appropriate wire size, overcurrent protection, and control devices for various motor applications. Understanding the different parts of Article 430 is essential for safe and compliant motor installations. For example, Part 3 of Article 430 covers motor overload protection. Motor overload protection is designed to protect the motor itself from overheating due to excessive current draw. This can be achieved using thermal overload relays or, as in our example, by properly sizing the circuit breaker. Part 5 of Article 430 addresses motor branch circuit overcurrent protection. This section specifies the maximum allowable size of the circuit breaker or fuses protecting the motor branch circuit. The goal is to protect the circuit conductors from overcurrent due to short circuits or ground faults. In the case of intermittent duty motors, the National Electrical Code allows for a reduction in the conductor ampacity based on the motor's duty cycle. This recognizes that intermittent duty motors do not operate continuously at their full load, and therefore the conductors can be sized smaller than for continuous duty motors. However, it is crucial to accurately determine the motor's duty cycle to ensure the conductors are adequately sized for the actual load. Another important factor to consider is the motor's locked rotor current. The locked rotor current is the current the motor draws when it is first started and before it reaches its full speed. This current can be several times higher than the motor's full load current. The overcurrent protection device must be able to withstand this inrush current without tripping, while still providing protection against short circuits and ground faults. There are different types of circuit breakers available, each with its own characteristics and suitability for different applications. Some circuit breakers are designed to handle high inrush currents, while others are more sensitive to overloads. It is essential to select the appropriate type of circuit breaker for the specific motor application. In addition to the National Electrical Code, local electrical codes and regulations may also apply to motor installations. These local codes may have additional requirements or restrictions that must be followed. It is important to consult with the local electrical inspector to ensure compliance with all applicable codes and regulations. When working with electrical systems, safety should always be the top priority. Always de-energize the circuit before working on any electrical components. Use appropriate personal protective equipment, such as insulated gloves and safety glasses. If you are not comfortable working with electricity, consult with a qualified electrician. Improper wiring and overcurrent protection can lead to electrical hazards, including fires and electric shock. By following the guidelines in the National Electrical Code and local electrical codes, you can ensure the safe and reliable operation of motor circuits. Remember to accurately determine the motor's duty cycle, size the conductors appropriately, and select the correct overcurrent protection device. Always double-check your work and consult with a qualified electrician if you have any questions. Now, let's talk about practical considerations when applying these National Electrical Code rules to a real-world scenario like wiring car lifts in a dealership. First, you need to gather the nameplate information for each motor. This includes the horsepower, voltage, full load amps, and duty cycle. This information is essential for calculating the correct conductor size and overcurrent protection. Next, determine the appropriate wiring method for the installation. This will depend on factors such as the location of the motors, the type of building construction, and local electrical codes. Common wiring methods for motor circuits include conduit, cable tray, and direct barrel. Once you have selected the wiring method, you can begin installing the conductors. Be sure to use the correct wire size for the calculated ampacity and install the conductors according to the manufacturer's instructions and the National Electrical Code. When installing the circuit breaker, make sure it is properly sized for the motor's full load amps and locked rotor current. The circuit breaker should be installed in a readily accessible location and clearly labeled to identify the motor it serves. After completing the wiring, test the circuit to ensure it is functioning properly. Use a multimeter to verify the voltage and current at the motor terminals. Also, check the motor's rotation to ensure it is rotating in the correct direction. Finally, document the installation. Keep a record of the motor nameplate information, conductor sizes, overcurrent protection device rating, and wiring method. This documentation will be helpful for future maintenance and troubleshooting. Remember that working with electricity can be dangerous. If you are not comfortable performing the installation yourself, hire a qualified electrician. A qualified electrician will have the knowledge and experience to safely and properly wire the car lifts according to all applicable codes and regulations. In summary, understanding the National Electrical Code requirements for motor circuits is essential for safe and compliant motor installations. By following the guidelines in Article 430 and consulting with a qualified electrician, you can ensure the reliable operation of motor circuits and protect against electrical hazards. Let's recap the key steps involved in sizing motor circuits and circuit breakers for intermittent duty motors as permitted by the National Electrical Code. Firstly, determine the motor's horsepower rating and convert it to watts. Secondly, apply the intermittent duty factor, typically 85%, to reduce the calculated wattage. Thirdly, divide the reduced wattage by the voltage to determine the branch circuit ampacity. Fourthly, multiply the branch circuit ampacity by 250% to determine the maximum allowable circuit breaker size for thermal protection. Fifthly, select a circuit breaker that is rated at or below the calculated value. Sixthly, verify that the selected circuit breaker can handle the motor's locked rotor current. Seventhly, choose conductors that are sized appropriately for the branch circuit ampacity, considering factors such as temperature rating and rating. Eighthly, install the wiring and circuit breaker according to the National Electrical Code and local electrical codes. Ninthly, test the circuit to ensure it is functioning properly. 10thly, document the installation for future reference. Following these steps will help ensure a safe and compliant motor installation that meets the requirements of the National Electrical Code. Remember, it is always best to consult with a qualified electrician if you have any questions or concerns about motor wiring. Additionally, understanding the principles behind these calculations can help you make informed decisions about motor circuit design and protection. For example, understanding the relationship between motor horsepower, voltage, current, and duty cycle can help you optimize motor performance and reduce energy consumption. Similarly, understanding the different types of circuit breakers and their characteristics can help you select the best overcurrent protection device for your specific application. By combining your knowledge of the National Electrical Code with a solid understanding of electrical principles, you can confidently tackle motor wiring projects and ensure the safety and reliability of electrical systems. Remember, electrical safety is paramount. Always prioritize safety when working with electricity and consult with a qualified electrician if you have any doubts. With the right knowledge and precautions, you can safely and effectively wire motors and protect them from overloads and short circuits. Let's consider some additional factors that can influence the selection of conductors and overcurrent protection for motor circuits. Firstly, ambient temperature can affect the ampacity of conductors. Higher ambient temperatures can reduce the ampacity of conductors, requiring the use of larger conductors to carry the same amount of current. Secondly, the number of conductors in a raceway or cable can also affect the ampacity of conductors. When multiple conductors are installed in the same raceway or cable, the ampacity of each conductor must be derated to account for the heat generated by the other conductors. Thirdly, voltage drop can be a concern in long motor circuits. Voltage drop can reduce the motor's performance and efficiency. To minimize voltage drop, larger conductors may be required. Fourthly, the type of motor controller used can also affect the selection of overcurrent protection. Some motor controllers have built-in overload protection, which may eliminate the need for separate overload relays. Fifthly, the presence of harmonics in the electrical system can also affect the selection of conductors and overcurrent protection. Harmonics can increase the current in the neutral conductor and can cause overheating of transformers and other electrical equipment. When harmonics are present, it may be necessary to use larger conductors and derated overcurrent protection. Finally, it is important to consider the future needs of the electrical system when designing motor circuits. If there is a possibility that the motor will be upgraded in the future, it may be wise to install larger conductors and overcurrent protection to accommodate the larger motor. By considering these additional factors, you can ensure that motor circuits are properly designed and protected for the specific application. Always consult with a qualified electrician or engineer to determine the best solution for your particular situation. Remember, electrical systems are complex and require careful planning and execution. Proper motor circuit design and protection are essential for ensuring the safety and reliability of electrical systems. In conclusion, understanding the National Electrical Code requirements for motor circuits, along with a solid understanding of electrical principles and practical considerations, is essential for safe and compliant motor installations. By following the guidelines outlined in this narration and consulting with qualified professionals, you can confidently tackle motor wiring projects and ensure the reliable operation of electrical systems.